Hey everybody, back for another session of getting into LabVIEW by using Project Euler.net, a website that gives you a variety of different mathematical challenges for you to explore math, optimization of math functions, and then for me to actually use languages to go ahead and, well, basically use it as an excuse to learn different languages. So hopefully we're going to learn a little bit more about LabVIEW. In the last session, it took like 24 minutes, but I kind of detailed out a variety of the little hacks and little tricks and tips that I was using throughout the process. So in this one, I'm going to choose to go a little bit shorter. So let's go ahead and get down to problem 2. All right, so we're going to start off with, in this case, let's see if I can get my head hidden out of here. We've got the Fibonacci numbers. And so what we're trying to do is for each new term in the Fibonacci sequence, of course, the adding 1 and 2 and so on and so forth, but considering the terms in the Fibonacci sequence who do not exceed 4 million. So basically go through, take all of the ones that are less than 4 million, actually less than or equal to 4 million, and find the sum of even valued terms. So basically add up all of the even numbers in the Fibonacci sequence itself. So let's go ahead and dive through. And in the essence of pure exposure or openness here, I've already gone through, and this is the reason it's going to be faster is I've already gone through and figured out the solution that I want in LabVIEW for this one, but I'm going to walk you through basically how I did it from scratch. Hopefully it's going to be a little bit more efficient. Okay, so one of the things that I found out is basically there's multiple different ways to calculate the Fibonacci sequence. Now, what we're going to do to start here is basically we're going to do a brute force implementation. We're going to find out that actually why every third number in a Fibonacci sequence has to be even and no other ones. And then indeed matrix exponentiation, which is a totally different way that I hadn't even realized until I went in and kind of realized this might be, this brute force is pretty slow. Maybe there's a faster way of doing it. So let's go ahead and dive into that. So for a brute force implementation of everything, we know that the Fibonacci sequence is inherently a iterative process. You take two numbers, you add them, you get the next one, lather, rinse, and repeat. So in LabVIEW, the way that you would do that is by using a for loop and then a few different shift registers. So let's go ahead and look at that. So I'm going to go ahead and do this using Quick Drop to make the video faster. Well, actually, we're still evaluating, we're still learning. So I'm going to do kind of a mix match. So let's go ahead. So I've got programming. I'm going to pin this structures palette down, and indeed the while loop, I'm going to go ahead and drop it down in there. Now, indeed, I know that I'm going to have to add two numbers, so I'm just going to go ahead and bring up Quick Drop, add, put that in the middle. So now the twist is I need to always add a number that is generated in the previous iteration of the for loop. And the way to do that within LabVIEW is by using something called a shift register. It is a construct on our diagrams with data flow. We're going to create or add a shift register. And we're going to take the output of the add and we're going to put it right there. And then we know that we're going to take that previous value from the add and put it right in. Now the twist with the shift register is that what we can do is we can take that last value and add it to the current value. So let's go ahead and do that. But wait a minute, what is our current number in this case? Well, there's initial conditions. In the Fibonacci sequence, you can choose to start at 0 and then add 1 and then have that add 1 and so on and so forth. And so there's a bunch of different ways you can kind of calculate all these out. But what we're going to do is actually use a feature of the shift registers that actually allows you to push in the initial condition of the shift register and its previous value. And so what we're going to do is I'm going to go ahead and create a numeric constant. Actually, since I know it's all integers, I don't really need floating point numbers. And I'm just going to put 1 and 1 as my initial condition starting parameters of my my shift register. And in actuality, what I'm going to do here is take those two values and push them in. Now, if we wanted to watch this run, did Norm do it right, and how does it actually look at the end of the day? Well, we can go ahead and we're just going to go ahead and double click and put a stop button there, and we're going to turn on execution highlighting. We didn't see that much before, but hopefully that'll give you the ability to see a little bit more. And in this case, we're going to use a new feature in LabVIEW that allows you to view it in a slow fashion. So we're going to watch it move nice and slow, and we get to see some of those values. So 1 and 1 comes through. Oh, let's see, maybe that didn't take the slow value. Let's go ahead and pause that. Yeah, that was still medium. There you go. So 55 and 34 makes 89. 89 comes through. And so you can kind of see, if I were to kind of, let's see if I can pause this right here. So the previous value here ends up coming around to the top value. And then this is the one, basically it's your iteration minus 1, iteration minus 2. So it's just, once again, the graphical syntax of what you have in LabVIEW and how it maps to things that you might already know. And so indeed, my previous two values were 1 and 1, and now we just go through and we can just let this run over and over again. There's nothing really too grandiose happening here. Now this is going to run for, unfortunately, forever, and we really don't want that. We only want it to run to up to and including 4 million. And so we're going to go ahead and pause this, or basically break the program right there, and we're going to add that logical condition in here. So we want to stop it when it is above or greater than 4 million. And so let's go ahead and just do that logic. If you remember from the last video, we're going to go to the comparison palette that we had before, and we're going to say greater, or actually just greater than. So there we go. So now we have the ability to say that, and we're going to go ahead and right click and say create constant to 4M. Now this is another neat thing about LabVIEW, is once again, we're used to working with, you know, data and scientific information, just kind of the nature of it. And so we understand we're not just a string. The large letter M next to the 4 means 4 million. And so we can kind of get away with some notation like that, and you'll see it expands it and things like that. And so now what we can do is we can actually, let's go ahead and just put an or in here, or throw that in line. So if I hit the stop button, I don't know how long it's going to take to calculate 4 million. Let's go ahead and just put that there. I'm going to go ahead and move that through. What did I miss? Oh, you know what? I must have wired it all to the same terminal. Let's go ahead and just get those all out. So I'm going to go ahead and do that. I'm actually going to use a feature that I didn't use much last time, where it was Control U. That gives me the ability, the exact same thing as this function up here, to clean up the diagram. And if you've got simple diagrams doing things like this, cleaning up the diagram can work pretty well if you change a couple different default parameters. So we can talk about that in another video, but basically it's underneath Tools and Options. And if you go down to the block diagram, you'll see here way at the bottom, there's some of the default settings for block diagram cleanup. I personally have found good success moving this to 25, 25, 25, 25, setting these away from their default, which is false, and then setting your manual tuning, and then setting your horizontal compactness to very low. And that allows you to get pretty well-spaced diagram up as opposed to what our defaults typically have within LabVIEW. So let's go ahead and hit OK there. That's fine. And now what we want to do is, well, we run this. Let's just see how long it runs. Once again, turning execution highlighting off. It runs nearly instant, fast, like what we saw before. But where's our information? Where's our values? Well, what numbers do we even have? Okay, so now that we've cleaned up our diagram a little bit, one of the things that you might be able to tell is that I've gone through and changed my output type here from the default. Actually, let's go ahead and just do that again from scratch. We're going to go ahead and wire that in, and what you'll see here pretty quickly is that the default piece of information that we've got is that the tunnel mode by default is the last value, or the last iteration of that effective variable. Remember, every wire is a variable that you didn't have to create a name for. But now we're going to auto-index on that, and now we're going to go ahead and right-click and create. Actually, we can just start the wiring process, right-click and create an indicator. And so now that we've got that indicator, you can see it on the front panel. We should be able to scroll down, run the program, and if I want to see the last value, same trick from last video, turn on that vertical scroll bar, and then go ahead and scroll down to the last element. And you can see indeed that we have greater than 4 million in terms of that list, because we have the indexing, but we're also, that last iteration is when the condition has been met. So we want to go ahead and only conditionally index things while this is false. So let's see. Now, if this is false, I need to invert the logic. I'm going to go ahead and let's go ahead and get out of this zoom mode. I'm going to press that control space and put not, and press control I. And what that does is it inserted on that wire the not. So let's go ahead and run that again. And very quickly, you can see that last element has disappeared. And we have all of the things. Now, these are all of the Fibonacci numbers from basically 2 going on forward. But really, we want to keep in mind, we want to start at that 1 and 1 up front, or even the 0 and, no, it needs to be 1 and 1. And so what I want to do is I want to add those first 2 elements in there for kind of a good reason. There's a couple different fun things we're going to do. So I'm going to actually add those elements into the array, and I'm going to do BA, or build array. Actually, let's go ahead and add it manually from the array palette. And if I go here to build array, put it in there, and now I'm going to go ahead and wire that in. I'm going to delete that wire, kind of insert it manually in line there. But what I'm going to do is I'm going to add those that element 1 up front. And the reason that I want to do this is, well, really for a couple, actually I'll add both of them in there like they're 2 separate elements, because I don't, I'm thinking about, hey, what if my program, if I want to start off at a different initial condition for Fibonacci, right? It's a little bit more flexible. And the reason that I wanted to do this very one specific thing is watch what I look at in all of the elements in the array here. this is something I found out after the fact. Look at the Fibonacci sequence. 1, 1, odd, odd, even, odd, odd, even, odd, odd, even, odd, odd, even. And that is a repetitive pattern within the Fibonacci sequence itself, where really I could go through this entire list and I can kind of brute force my way through what is available. And let's go ahead and finish that off, but you're going to see why that's important in a minute. So I'm going to take that array, I'm going to kind of move it out of the way. It's just a piece of information. But now I need to create another filtering algorithm that says whether or not it's even. And to some degree, heck, I could probably put that in that exact same loop. And you know what? That's probably the right thing to do. No, I'm going to leave it outside. I'm going to do that filter so you can see different things in terms of the iterative approach and then also the once again, the filtering of even values. So I'm going to go ahead and do another for structure, and I'm going to go and put that in here. And for each one of those elements, I'm going to do a quick test to determine whether something's even. And if you remember from the first one, quotient and remainder is a great way to tell if something is an integer multiple of something. And so I'm going to go ahead and put that value of 2 there, and every time the remainder is indeed equal to 0, presuming that 0 is not in the list, we know we're going to have an even number on our hand. So I'll do equal to 0. There we go. And so that's from the comparison palette that we had before. And now I'm going to take that number right there, push it on through, tunnel mode, conditional, and then I'm going to do add array elements, but I'll go ahead and show you where that is. Once again, on the numeric palette, there is the add array elements specific item, and I'm going to go ahead and run that. There we go. And so there is our very specific sum for our brute force. Actually, you know what? I'm going to go ahead and get rid of that and just wire my brute force indicator into it right there. There you go. So now I can see that I indeed have brute force available. I'm going to go ahead and check that value. That looks pretty familiar to what I came up with before. So I think we have the right math available there. Huzzah, we got it. Perfect. All right, so next up, we're going to do the optimized thirds. And now you'll start to understand why I kind of wanted to have this array external to everything. Because now I wanted to show you another neat trick within LabVIEW is that if you know that you need a subs, like every 4th element, every 12th element, every whatever, usually for smaller numbers, but basically there's a function, not basically, but there is a function within the array palette within LabVIEW called Decimate 1D array. Let me go ahead and see if I can bring some context help up here for you. There we go. And so what this is going to do is give you the ability to see, hey, I want element 0, 1, 3, and then multiple iterations of that. So if I wanted every 3rd element of this one-dimensional array, I'm going to go ahead and decimate that array. Let's go ahead and get some of the stuff out of the way here. And now, instead of summing all the numbers and needing to conditionally filter, I'm just going to go ahead and use that exact same tactic. Once again, feel free to go ahead and use elements that are already on your diagram as palettes that you didn't have to right-click and go navigating through, or even type in quick draw. So now that I've got that there, let's go ahead and check out the optimized thirds. Run that right there. Boom, I've got the exact same number. Now I could have done the same thing, like once again, in that for loop, but I kind of like the idea of showing these two things separate. All right, now we're in this last stage where we get particularly fancy, where once again, the idea of calculating a higher order number Fibonacci value is effectively a costly thing because you have to calculate all values leading up to it. Now, for our specific situation here, that makes a lot of sense because we have to add up all the even numbers leading up to it. But it led me down a rabbit trail, once again, called matrix exponentiation. And matrix exponentiation gives us the ability to calculate any value of Fibonacci without needing to do all of the iterative math leading up to that point. Rather slick. Now, I'm not necessarily a mathematician, and some of these things still elude me in terms of understanding it, but you can see how complex kind of the Python code gets here. It's not too bad, but it's actually not too bad in general, but it's going through and doing that math to go ahead and just calculate that matrix, the matrix exponentiation. So instead of going that route, once again, what it's showing is, if we were to scroll up here, is if I get to slide 7, there we go. If you want to calculate basically f of n, you can go through and take this quasi, it's not really an identity matrix, but this matrix right here, and you raise it to the power of n minus 1, and you can go ahead and get your, and then eventually multiply that times the individual value of 1, 0, and you will get your values out on the other side, which is pretty surprising to me how easy that was. And luckily within LabVIEW, we already have the ability with once again, the language of LabVIEW is purpose built for scientists and engineers. So there's a lot of constructs and things already part of the environment and the tool and so much. Once again, it's an engineer's workbench in the acronym on purpose. Let's go ahead and minimize that there. So what I should be able to do, if I don't screw it up here, is I can go through and I'm going to take that initial matrix that we were looking at just a moment ago. So I'm going to kind of create, I'm not kind of going to, I am going to create a two-dimensional array that is, once again, the 1, 1, 1, 0, that same type of matrix we saw before. I'm going to go through, and you can do that a couple different ways. Let's show. So if I wanted to do that manually, I could maybe take that constant on the block diagram. You can actually take a constant, right click on it and say change to array. So that's a nice thing. So you can take any value or any array. You can actually go back from an array back to an individual element. So we don't need to worry about that. And then if you wanted to expand the dimension of the array as a constant on the diagram, it's merely a matter of dragging that terminal down right there. And now you can see that we have a two-dimensional array available for us. And so once again, that's the, hey, how are you working through this language? Which features are giving you good value for quick and easy creation of constants and variables with no syntax necessary, except you just have to remember a little bit of the mechanics. So we've got that kind of identity matrix in there. Within here, you've got the real matrix. And so I wanted to figure out, hey, what's this function name again? I see that question all the time. If you bring up context help, you'll see where this exists here. If you wanted to see it on the diagram, you can go to visible items and show the label for it. So array to matrix.vi. And the other way that if you have a name, a way that you can find it is if you right click, and in the upper right hand corner here, you can see that we have a search capabilities that showed up. And now what I can do is I can type in the array to matrix and it will show me where it is. So array to matrix, there we go. So now if I were to go ahead and click on that, it will show me in the palettes where it is. And it turns out that it's underneath the programming and array palette. That down here, I can take any two-dimensional array and turn it into a matrix, which there's a good reason why we want to do that. And it's because we have a very specific matrix exponentiation function that's already available for us to use. So if I were to go to the mathematics folder and I want to go to linear algebra, let's go ahead and pin that down. And then what we're going to be doing is looking for the icon that looks like an exponent next to a matrix. Surprise, surprise. There's to the -1. And there we go, right there, matrix power. And so now what we're going to do is take that matrix power, put it right there, put that in the loop. And if I were to go ahead and put any number in here, let's just go ahead and, I'm going to use a great debugging tactic. Like I want to figure out how to use this function. So I'm just going to, it's so easy to just create a brand new program with a user interface and interact with that. It's just mind blowing how nice it is. So I'm just going to basically, I'm going to cut it out of that program right there. And I'm going to go ahead and create a brand new VI, paste it, and I'm going to just kind of use that same run continuously tactic that we were messing with a little bit last time, where I'm going to go ahead and create a new control, and then I'm going to go ahead and create a indicator right there. But the twist is I want to be able to get a sub element out of that matrix. So I'm going to go ahead and get the matrix sub element out of it. It's in the array palettes actually. And so now I'm going to go ahead and create an indicator for it. And if I were to just run this program, you'll see once I move this up to 1, actually, let's go ahead and get some things a little bit closer together here and get us zoomed in. It'll run continuously and 1, 1, 2, 3, 5, 8, 13, 21, 34, on and on. So a single function within LabVIEW gives us the ability to go ahead and get rid of that matrix out of there, gives us that easy ability to go ahead and calculate any specific number. Now what we're going to do is we're going to combine this power of being able to get any value also with that recognition that we want to get every third element out of it. So how do we go about doing that? Well, let's take this initialization matrix and move it to the outside. And then we're going to go ahead and put these things inside of a while loop. So while structure, WS is the quick drop keyboard shortcut way of getting there by default. I'm going to get rid of that. And then by default, I would want to wire this in. But of course, this is going to get me all of the elements out. Actually, let's go ahead and, let's go ahead and do what we want to do. And for the sake of the video is I'm going to use something very slick as I want to get every third element. So as the end iteration goes from 1, 2, 3, 4, I want 3, 6, 9, 12. You get the idea. So I'm going to use something great, I hope you're listening real close on this one. In the math palette, or the numeric palette, sorry, there is a tool right down here in the bottom right-hand corner, expression node. So wonderful, because it allows you in a very compact syntax within the LabVIEW diagram. Keep in mind, when I say syntax, I mean graphical syntax. It's the visual representation of it, that I can just do 3 times x, and I can, and at that point in time, now I have the function doing everything. It's doing exactly what I'm looking for. Now the twist is on here. Now the other thing that I need to do is I don't want to start off at 0. I want to start off at the first, because it's 1, 1, 2, 3, and that's every third one that you've got from there. So I really want to do x plus 1. So I'll put some parentheses in there to be a good steward of my order of operations. There we go. So now that should get me all of the individual elements. But the other thing that I want to make sure of is that I want to keep only elements that are, once again, that less than or equal to 4 million. So I'm going to go ahead and create this, move this out, 4 million, wire that on through. And then I'm going to do also something different, because if you noticed, I used kind of inverted logic than what I used last time. And so I used something where I am only going to, let's see, less than or equal. So this is going to be true, 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 true. Well, by default, this part of the structure would stop it at the very first iteration. But if I use the operate finger, I can go ahead and flip the logic on the for loop very quickly, and it's going to run as long as that is true. The minute it's false, it's going to stop the loop, for which I still need to go ahead and do that tunnel mode, indexing, wire up. Now, interestingly enough, I've had that same situation before where it's a single element, but I want an array. So what should I do? Well, I'm going to right click, change to array. Boom. Program's not broken anymore. Love it. So now I'm going to go ahead and right click tunnel mode, conditional. And now I don't need that not logic, that inverting logic in there. I've kind of taken care of that inverting logic on that. So let's go ahead and see what we get when we run this. Hey, that looks like an even number to me. Let's go ahead and visible items, vertical scroll bar. Well, actually, with an array, when you put it on the front panel, you need to scroll down and make more elements vertically. Otherwise, it's going to try to make a horizontal scroll bar. And so now I'm going to go see the vertical scroll bar. And now I can scroll down. Those all look like even numbers to me. And you can see a little bit of auto formatting right there. Let's see if I expand it out a little bit, if it's going to show, though. No, it's more large enough. But now we've got that. So now what are we going to do? We're going to take that. Well, let's go ahead and just take this entire chunk of code that we know works. I'm going to cut it from here, put it into the other program. And one other thing that I notice is that I know that the output is always going to be an integer. So I'm going to go ahead and do a little bit of simplification. How do I convert from one data type to another? Well, I can go to the numeric palette all the way up here, go to the section that you can see right up there. And I just realized my face might have been covering up some things that you all were looking at before, but I can go to I32, or long integer. I can put that right there, put it in line. I could have done an insert like what we had before, and voila. Now we've got a program that we can have go. And then another thing is like, well, that's still a double. So maybe that's more data than what we need. Well, I can right click representation, and you can't see over there. Let me go ahead and see if I can move it over a little bit. Right there, representation, and go to I32. And now you can see that all of the data types line up very nicely. Run that one time, it looks okay. Let's use that same sum or add elements that we had just a minute ago. And let's go look at matrix exponentiation. And hey, look at that. We have all of our values indeed lining up, all with different mathematical ways of going about doing that within LabVIEW. So let's recap real quick what all the different things that we look through. We can look on the diagram. What are some of the different elements? All right, so now on the diagram, once again, you'll have to forgive, a clean diagram is a happy diagram. And so what we're looking at here is not as clean or happy as it should be, but I'm trying to move fast for y'all so you don't fall asleep on me. So let's go ahead and look at what we've got. We've got a few different things that we were looking at. We saw that the shift register. That's a way of carrying one piece of information from an iteration of a loop to another. If you were using text-based languages, you would have needed to create a variable of some sort and dealt with cleanup and scoping and variable names. Not the case in LabVIEW. The shift register is the syntax that gets you that ability. You also have the ability to expand this down to n number of elements within reason to get the previous n number, so n-1, n-2, n-3. But keep in mind, you also have to initialize those values to something logical. We can talk about uninitialized shift registers in another video. So we worked through the logic here. We reuse that ability to do a conditional indexing, but usually that indexing you will see on a for loop. So for X number of iterations, you're either iterating across or you're building up each one of those times. Well, in this case, what we're going to go ahead and do is we're going to use it on a while loop, which is a little unorthodox because usually while loops run for a long time, but we know ours is only going to run up to a very controlled condition, not like for the entirety of the given program. The other things that we use is we reuse this logic for kind of filtering multiple integer multiples of a thing. And then we also introduced a new structure here, or a new primitive, which is the Decimate 1D array, which allows you to get only every nth element out, once again, within reason. Now, there are functions within LabVIEW where you could say, not by merely expanding that node, you know, if you needed every 38th element, you wouldn't want to expand this. It's not a scalable implementation. And indeed, there is a primitive within LabVIEW that allows you to be able to get every 38th, but this is kind of the quick and dirty. This is the way most of us out there in the world will go ahead and do it. So now we have two different ways to do it. And also you learned that in the Fibonacci sequence, every third element, starting at 1 and 1, turns into an even number. And if you stare at the series for a minute, you'll realize an odd number plus an odd number equals an equal plus an odd is an odd. You get the pattern. So, and that's kind of how that every third element. And then the last one that we learned about is we went into realizing that in LabVIEW, once again, we are a scientific and engineering tool. We know that matrix math is used all over the place, similar to MATLAB. And so the idea of matrix math and linear algebra is a natural part of the language at this point. So we can take a two-dimensional array, turn it into a matrix. We have specific functions already ready to go to do the matrix math for you instead of you needing to go out and find various different math-based libraries. It's part of the tool, your engineering workbench that you get with LabVIEW. We get the information out and we get the same result. And then lastly, we saw a very neat little trick where you can go ahead and change the logic on your while loop to be do it while false or stop when true or continue while true, which of course we still need to be able to take advantage of that conditional based on that last iteration. Very, very common source of bugs when you're doing these types of things. All right, so that wrapped up the bigger picture of everything. I hope that gave you, once again, a little bit of insight on how to, of Project Euler. And, once again, this is prior art that I have no association with. That was recommended to me by Becky Linton, an esteemed member of the LabVIEW community, and she uses it for her students that are either in middle school or high school with FIRST Robotics as a way, once again, of learning the language. So if you're watching this and you're part of Becky's group, thank Becky for me. And then indeed, hopefully this gave you a deeper insight as to constructs that you might use in other languages and how it maps to LabVIEW as an ecosystem. All right, and I'll take that away and let's go ahead and put a pin in it for the night, and I'll see you in video 3. Thanks.